we're talking about pushing boxes right now, I guess, and doing work. So last time we were talking about doing work, and we are talking about how force and displacement and angles and things were involved in that. This time we've got a box that's being pushed along a horizontal surface by a force that's 95 newtons. So maybe I'll just take note of what I know. I've got a push force. I'll just call it a pusher. I'm not even going to call it an applied force, but it is, I guess, of 95.0 newtons. And the velocity is going to be constant. So it's moving along at a steady speed. And we've been in a situation like that, where you have an applied force going this way, and maybe there's a friction force going this way. And if those two balance each other out, and the normal and the FG cancel each other out or balance each other out, then this thing's going to move along at a constant velocity, right? Because acceleration will end up being zeroed out because net force is zero. So that's kind of our string of thinking with that, okay? So here we've got this mass that's being pushed by 95 newtons, and let's just say that it's being pushed to the east. Now in terms of our reference frame, it's okay to say east is this way, and up is this way, and down is this way, and this is west. This is a side view of something that's getting pushed to the east. Of course, friction would be acting to the west. So this is not an overhead view. We're just saying that forward is east this time, okay? And that's totally fair game. Up, down. All right, cool. Anyway, so this pushes to the east, and velocity is constant. The box is displaced by 16 meters to the east, so delta D is equal to 16.0 meters east. Now, if this thing is moving at a constant velocity, what's the acceleration?
Zero.
Zero, all right. Acceleration is 0 meters per second squared. If the displacement is to the east, actually, let's just sketch this out. I got an applied force or push force going this way. I've got a displacement. Notice I never attach my displacement vectors to the object. They're always kind of separate. I got that habit from free body diagrams once before. But if I look at the push force and the displacement force, what's the angle between those two vectors? What's the theta value? Are they going in the same direction?
Yeah.
If things are going in the same direction, what's the angle between them?
Zero.
Zero. Yeah, 0 degrees. We say it's 0 degrees. And the way that we're kind of rationalizing that is that when we talk about things that are going in the same direction, we say that force and displacement, those two vectors, I'll put arrows on top of them just to emphasize that they are vectors. When they're going in the same direction, we say that they're collinear. Their direction that they're pointing in is the same, collinear. We could say that they're parallel to each other, but they're in the same direction, okay? Another thing that I want to think about, just while I'm kind of thinking about ideas related to the basics here, something that I remember learning when I was in math class, and I'm sure that you learned it too, whether you remember it or not. So I don't know if you don't remember it, I don't know if you really learned it, but let's just see. If we talk about the cosine curve, remember how the cosine curve looks? Starts off high, goes down low. That is how the cosine goes. So it goes down low and then it comes back up again. And then I know that that low point, what angle does that happen at? Do you remember? Is it 180? 180, yeah. So this is 180 degrees. That means that this happens at how many degrees? 360. Back here, this happens at 0 degrees. And so that's the unit curve for the cosine. We just say that it has an amplitude of -1 at 180 degrees, and it has an amplitude of +1 at both 0 and 360 degrees. And so keeping that in mind, and that just as a quick little thing that I should have in my head, if I've got a theta of 0 degrees, notice that's going to correspond to this curve if I'm going to do cosine of that angle. The only reason I bring that up is because we're going to have to calculate the work done by this pusher, and the work done by the pusher is equal to force times displacement times cosine of the angle between those two vectors, force and displacement. So I've got my force, 95 newtons. I've got my displacement, 16.0 meters. cosine of, since they're collinear, 0 degrees. As soon as I see that 0 degrees, I'm going to save myself some keystrokes. What's cosine of 0? 1. Every single time it's 1, okay? And that's kind of the magic of collinear things, is that term drops out. And if you did calculate work when you were a kid, like when you were in elementary school, most likely the teacher, whether they knew they were doing this or not, eliminated the cosine theta from the formula by just making it be an invisible 1, right? And most elementary school teachers probably skip over this little lesson. But if you did get lucky and you had a science teacher in elementary school that was committed to the curriculum and really wanted to like make sure you got the idea of energy and calculating things in science, then they would have done this for you, okay? And you can see where a kid could totally have managed this, right? And if you didn't get the chance, then believe in yourself. You could have done it, right? You're just multiplying these two numbers together. So we would get this force value, maybe from like a Newton spring scale or something. We would get this distance maybe by using a meter stick. And if I was a grade 7 kid or a grade 6 kid, I could have done this math. And this would have been a great introduction to how to do basic work calculations, right? Anyway, 95 times 16 ends up being a nice round 1,520 joules. Because as we said before, newtons times meters gives us joules. And just in case you missed it, Newton is kilogram meters per second squared. And if I multiply that by meters, I'll end up getting kilogram meters squared per second squared. And that's the definition of a joule. Okay, so definitely you're getting joules out of this, but also we just know that work is an energy measurement, or measured as energy. So we calculate this. It looks like I only have 3 sig figs here, so 1.52 times 10 to the power of 3 joules is the best way to round that guy off. I'll put a little approximately equal to sign over there. And I could say, therefore, the pusher does 1.52 times 10 to the 3 joules of work. And this is like a work measurement that we could have built into a lab that we did in the past. Yes? You know what? I guess I didn't really have to because I didn't round away anything material there. I'm just in the habit of doing that every time I round off to sig figs. It's kind of like my indicator visually for me that I've brought it in line with my significant figures. Yeah, I don't have another communication tool for that, you know? You're right, I haven't really rounded anything away there, but it is sig fig friendly now. Is that what your question was too? Yeah, that's a fair question. All right, so what are joules? I've kind of hammered this home, but let's put it in a more like not in the margins place. Force times displacement times cosine theta. If I'm breaking this down for dimensional analysis, which is what we call unit analysis, force contributes newtons, displacement contributes meters, cosine theta contributes no units. Newtons is defined as kilogram meters per second squared. Meters is just meters. And that becomes kilogram meters squared per second squared. Maybe the exact same thing as I wrote before, but not squeezed into the margin. And that is that definition of joules. And there's always somebody that asks, does the J have to be capitalized for joules? Yes, because it's somebody's last name. And so we write it as just J when we're using it in calculations. And so this is like our shining joule.
Shining joule.
Okay, ha ha ha. Yeah. All right, so positive versus negative work. So what we just talked about just now was positive work. And so I want to just pose the question, what is positive work?
Oh, negative work.
So positive work is when you give energy to an object. Could be to an object or system. So I might ask you, you probably could guess, what is negative work?
Takes energy away.
What do we say?
Takes energy away from an object.
Got the answer. Takes energy away from the object. Does that seem like a reasonable opposite? Yeah. So taking energy away from an object. or system. Sometimes people will phrase it as losing energy. So energy loss. Okay, I got like a cute little cartoon there where somebody's changed the text of the original, because I don't think Kelvin and Susie ever said this. But what do you call someone who steals energy from the museum? Womp womp. Okay, anyway. Jewel thief. All right, so here we got a hockey puck. And hockey puck is shot so that it slides along the ice for 50 meters. Okay, so right away, I'm going to say, looks like we have like a left-right kind of situation here. So this hockey puck is traveling along. It's going to travel towards the right. Here's the left. Left is going to be, or sorry, right is going to be positive. Left is going to be negative. We're going to be traveling for 50 meters. So let's just say that we go positive 50.0 meters. And this hockey puck is shot so that it slides. Okay, we know that hockey pucks, as they slide, if I'm thinking free body diagrams, I know that there's a normal force holding it up. I know there's an FG pulling it down. I know that there's friction working against it. Is there any force working in the direction of travel for a hockey puck? Answer no, right?
Just the second it's hit.
Yeah, after it leaves the hockey stick, it's just sliding. It's got its speed, but it's slowing down to a stop. Ever since it leaves the hockey stick, it's slowing to a stop. So this is the free body diagram. So I haven't thrown that out just because I'm talking about energy here. And we say that it has a mass of 10.0 kilograms. And the ice has a coefficient of kinetic friction. Oh my goodness. I really can't forget the previous unit, 0.500. What are the units on coefficient of kinetic friction?
No.
Unitless, right? Remember how we got that before? So how much work is done by friction on this puck? Well, gosh, I haven't been told what the friction force is yet, but according to this free body diagram, I've got some figuring to do, right? So I can say, hey, I know that the magnitude of the normal force is going to be equal to the magnitude of Fg. That's not in doubt. So the magnitude of mass times acceleration due to gravity, which is 10 kilograms times 9.81. Notice it's the magnitude, so I'm not worried about negatives on that 9.81. But I chose a 10 kilogram hockey puck, not because it's realistic, but because it's easy for the math. Okay, that's a hockey puck. That is a serious hockey puck. If you know what 10 kilograms is, nobody's using a 10 kilogram hockey puck. So if you noticed that earlier, yes, it's not realistic. 98.1 newtons though of force. Now if I wanted to use this, what would I use this value for? To calculate what? Yeah. Got it. So now I got my normal force. I'm ready to calculate Fk. So I'm not totally in love with the shape of my flow of thinking here, but okay. UK, F normal. And if you need to do these little flow arrows for yourself, not just for your own thinking, but maybe for the marker, it's okay to do, but it actually really does help for your own thinking, especially when you go back to look at your notes or look at like what your homework was or whatever to try and learn from yourself. Because believe it or not, the things that are fresh in your mind now won't be fresh in your mind come exam time. Can anybody do that math again? I kept the numbers round. What's half of 900 or 98.1? What was it?
98.05.
No, it's not 98.05.
49.05.
49.05, yeah.
Words are not coming out right now.
49.05. Now that's going to be the magnitude of the friction force, for sure. I know that my free body diagram tells me that it's to the left, right? So it might be a negative direction if I was thinking about reference frames. But remember, when we talk about energy calculations, we don't have to care about reference frames. So I'm going to cross that out. We don't have to worry about reference frames when we do energy calculations. I drew it because I was working just like on my natural drive from the dynamics unit, but we don't need to care about it when we're talking about energy calculations. The question that we're trying to do is figure out how much work is done by ice on this thing. So I'm going to say, all right, well, oops, I didn't mean to write an F. Ah, nuts. I had a whiteout here. There it is. All right. I meant to write a W. W. So the work that's done by kinetic friction here is going to be Fk, the force of kinetic friction, times the displacement, times cosine of the angle between those two vectors. And if I think about I did draw a free body diagram. I might have thrown the reference frame out, but if this puck slides towards the right, doesn't that mean that its displacement is this way? What's the angle between that force and that displacement?
180.
What is it?
180.
180. Look at that. Hey, even if you don't see it immediately, let me draw it again. If I were to draw the displacement this way and the FK this way, I'm not adding them tip to tail. I'm just trying to compare what the angle is between the two of them. One's pointing to the left, one's pointing to the right. The angle between them, that's 180 degrees, right? That's what even though they're not like side by side in my picture, the angle between them is 180 degrees if I did put them side by side, okay? Now there's a name for that. If pointing in the same direction is collinear, this is antilinear.
Oh, there's a name.
Yep. You know, like ancient people thought that if you could name a frightening thing, then you had ownership over it. You know, like if there was something frightening in the bushes and you could give a name to it, you had some power over it, right? And so here you go. If you have names for things, you know, knowledge is power. That's good. So antilinear, 180 degrees. I shouldn't say ancient people. There's people today that think that, and I think that. I call it antilinear. Now I know. All right. So FK, we had an FK value of 49.05 newtons, not even rounded or anything. Displacement was 50 meters. That's kind of a long slide across a hockey rink, but okay. Somebody with a calculator help me out. Oh, wait a minute. I forgot. Cosine of 180. Now, before I do anything with my calculator, you could put it in your calculator, or I could go back up to this unit curve. What's cosine of 180 going to be? -1. Look at that. So I could put it into my calculator, but I know, because I know how the cosine function works, cosine of 180, anything that's antilinear, is just going to throw in an extra -1, okay? Which obviously you can see how this relates to positive and negative work. You guys see the connection on this one? All right, so what's the magnitude going to be, though? I know it's going to be negative, but 49.05 times 50. Yes, sir?
2,452.5.
Nice. 0.5, and then it's newtons times meters, which we already said is what? Joules, yeah. So we'll leave it as joules. You can go straight to the joules. You don't have to write the Newton meters. And then if I was going to round this off to sig figs, then I could say, okay, well, looks like I only had 3 sig figs here. So negative 2.45 times 10 to the power of 3 joules. Now the way I would frame a therefore statement, I could say, therefore, the puck, you know what? I don't like, and you know what, this is a stylistic thing. If somebody says, I do so many joules of negative work on you, doesn't that seem like a weird way to say it? And the reason that I say it's a weird way to say it, if I go to the bank and somebody says, the bank gave me $500, that makes sense. They gave me $500. The bank gave me $500. If I go to the back alley behind the bank on my way home and I walk down that back alley and somebody pays me -$400, what have they really done to me?
Take your money away.
Yeah, they robbed me in the back alley, right? And so I don't want to say that the ice did this much work. I would like to say that the ice took this much energy, right? It's not wrong to say that it did negative work, but this is a style thing, okay? And you're going to run into this. So it's not just me that talks this way. Lots of people talk about objects losing energy to their environment or what have you. But yes, the environment is doing negative work. But it's really getting robbed in the back alley here, okay? All right, so we've got the puck loses 2.45 times 10 to the power of 3 joules to the ice. Alternatively, somebody could have said, therefore, the ice performs negative 2.45 times 10 to the power of 3 joules of work on the puck. Those are equivalent statements. I'll tell you, I like the top one better. Okay? You get get the same marks either way. But people are going to tend to think like the top one, right? They're going to talk about energy loss, not getting paid in negative dollars. Is that clear to everybody? All right.
Forgive this